Welcome back. So this presentation here is part of the DFT course, but it's labeled slightly differently as I'm going to provide a number of screencasts, which would be more related to the DFT in practice. And so that's a little bit different from the quantum theory or from the fundamental DFT theorems and stuff like that. So these are things that are useful when you do calculations. And in this screencast, I'm going to talk to you about basis sets, which is actually very important in our case. So here's an example on this slide where you can see a wave function. It's in a box and it is described on a grid. You can clearly see the grid, and this is how we represent the function. Of course, on a computer, you need to have a representation of the functions that you have. So grid like this one that you can see on this example is fairly usual. I mean, this is something that we learn first, is to discretize functions. So this is the possibility. But there are other possibilities which are very often more efficient to represent wave functions and densities and potentials, which do not rely on grid, but rely on different approaches, and that's what we are going to do in this screencast. So we call that a basis set. So a basis set is going to be that object that will allow us to represent the different properties like wave functions, density, and so on and so forth. And because of the specificity of the DFT problem, those basis sets will depend on the kind of problems that we want to do. So we have two aspects, of course. We want to have a quality of the solution, and at the same time, we would like to do it at a computational cost that's bearable. So of course, we have two aspects here, and as always, those two aspects are kind of go against each other. First of all, we always want the best accuracy possible, but at the same time, we also want to have a calculation that's done in a time that's reasonable, and or even more than time that's reasonable. Actually, it's feasible. So there is not just a matter of time, but it's also a matter of memory sometimes. And this is what we are going to do. So we are going to explore the compromise that we can get between accuracy and computational aspects. So the slides I'm going to show you now, some of them are pretty heavy because I'm not going to read them all in detail. I'm going to provide you the summary of that, and you can always have access to the slides using the link that's provided on YouTube. In the slide, I'm going to provide you information that will be useful when you have to make a decision, but I'm going to give you pretty much the overview of the state of the matter. But before we actually talk about basis sets, there is one aspect that we have to take into account when we do density functional theory, especially for crystals and surfaces and so on, is the effect of pseudo-potential. That's actually an essential one. So imagine for a second that you look at the bottom picture on the left, and you know that we are going to have a nucleus, and sometimes we have many electrons in the nucleus, and most around the nucleus, of course, and of course all those electrons that are around an atom, for instance, many of them are not going to participate to the chemistry, and they're not going to participate to the bonding. They're not going to participate to reaction, or even when you deform your structure and you want to calculate mechanical properties, for example, or when you want to look at an STM image, or all those things, the innermost electrons, the one we call the core electrons, do not participate to most of those effects. It does happen so that we have to take into account the inner electrons for some particular applications, but most of the applications that we encounter in material science do not. So why is that? Why is that important? That's important because there are two aspects. The first aspect, of course, is that those electrons that are the core electrons, the ones that are closest to the nucleus, and of course they are the ones that have the lower energy, in all the spectrum. And that's why they have so low energy that it's not easy to excite them. That's why they do not participate to the chemistry. Um, there are many of those electrons. And so we don't necessarily want to solve the Cohen-Cham equations for all those electrons. So we'd like to reduce the problem to fewer electrons. That already helps from a computational standpoint. But there is another aspect, which is the serious aspect, and you can see that on the plot on the left for the all-electron wave function plot. Those electrons are well localized around the nucleus, and as a result, the variation of the density for those electrons is very sharp. And when you have something that's very sharp, it's always more difficult to represent it on a computer because, for example, imagine you have a grid. If you had a grid, you need a very fine grid to represent those electrons that are very sharply localized around the nucleus. So historically, the development of pseudo-potential was a key aspect to actually do not worry about those. And of course, you can see here the connection with basis set because, of course, if we do not have to worry about those highly localized electrons that are core electrons that are inside, then maybe we don't have to have such a fine grid, for example. And there will be probably another screencast on pseudo-potential. What I'm providing you here is just enough information to understand this aspect with respect to the basis set. And what people have done is that to replace the problem on the left to the problem on the right, where there is an effective core. So an effective core is the naked nucleus plus those core electrons. And what scientists have done is to develop a pseudo-potential, which is a potential which is exactly the same as full potential outside a certain cutoff, a certain radius cutoff. And so everything that happens outside that cutoff everything behaves just as if we treated everything, but inside a potential is modified so that the wave function inside the cutoff is now smooth. So you can see that with the blue trace. So long as you do not excite the electron inside the nucleus, you do not have to worry, inside the cutoff, sorry, you do not have to worry about them. And just to be clear, just to be complete, those electrons that we are going to treat, so those that live outside of the cutoff, those electrons are known as valence electrons. Okay, so this is the idea, and there have been a lot of development over the years. People started with norm conserving pseudo potential. So these are potentials that keep the number of electrons correct, keeps the norm. And then there were those important developments, for example, from David Vanderbilt in ultrasoft pseudo potential. Ultrasoft because the softer the easier it is to represent and the behavior when you do finite differences and so on. So pseudo-potential is an important thing. I would also note that pseudo-potential are not used in quantum chemistry most of the time because they use a different kind of basis, which I'm going to discuss in a minute, which allow for the description of the inner electrons. But even in quantum chemistry, you do have sometimes the effective core, which is it's not exactly a pseudo potential, but it also basically it's the same fundamental idea. So we do not treat the core electrons because they are very localized, and those electrons do not participate in chemical processes. Therefore, we do not worry about them. So this is a pseudo potential. That's actually important. Now, in the old days, when you were doing a calculation, you had to build your own pseudo potential. That was a bit tricky. There were code existing and many people developed those. Now, most of the code that we use come with pseudo potential. And those sometimes there's more than one pseudo potential for a given atom. And because they include a different number of electrons. So you have to worry about that. And it's particularly true for the bigger atoms. Where you can add some of the electrons are treated as core, those are treated as valence, so it's important to do that. But in general, this is a concern that maybe existed very broadly, maybe 15 years ago or 10 years ago, but it's not a concern that is deep. But do not forget when you do calculations that you have also that approximation essentially. So let's now talk about the main types of basis set. So the first basis set which has actually led to, in fact, Popple winning the Nobel Prize in Chemistry, is the development of Gaussian basis sets. So the Nobel Prize in Chemistry along with Walter Kohn. What is interesting about Gaussian basis set is that we can develop many of them. I'm not going to read all the details here, but those different basis sets are well known by chemists. I mean, you would need a full screencast for that, and I'm sure you can find one on YouTube about the Gaussian basis. You can learn about this separately, but the idea is essentially that you represent your orbitals and your density as a linear combination of Gaussians. And as you know, Gaussians are always your friends because Gaussian are easy to integrate. This is one of the functions that's the easiest to integrate, even if it's when it's used as a kernel, so times another function. And another advantage of Gaussians is that they've been tested by hundreds of thousands of calculations, or maybe more. So they are very well tested. And when something is well tested, usually this is a good choice because you would be able to use them yourself, and you don't have to redo tests that others did. So this is an advantage. The thing is, Gaussians work really well when you do chemistry, when you do molecules, and even large molecules. One thing that's really maybe an issue is that when you want to be really, really accurate, you need a lot of Gaussians, and it becomes a computational bottleneck. Another fundamental aspect is also that you cannot systematically improve your basis set. I mean, this is actually not exactly true. There have been people like Dunning and others who have actually developed methods to do a more systematic understanding of convergence of basis set. But this is not like a continuous and systematic improvement of the basis. So this is something that makes it a little bit more complicated to do convergence studies. The most popular basis set for solid state physicists and material scientists in general is a plane wave basis. In that case, this is essentially representing your system with a Fourier transform, if you will. But of course, a Fourier transform will usually be an infinite series. And of course, since we do this computationally, it's going to be a finite series. So in that case, we actually use a certain number of plane waves and we stop a certain number. I'm going to discuss that more in a few minutes. So this is actually more systematic because if the series converges, the more basis we add, the basis sets, the more basis or the number of plane waves we include in the calculations, the better the calculation. So this is actually good for convergence studies. Now, the problem with plane waves is that they are not great when you have lots of vacuum. Why? Because you are representing essentially the vacuum the same way as you represent where there are atoms. Plane wave are, of course, totally delocalized basis. So they can be very computational. They could be computationally very costly. So you can use plane waves for atoms and for molecules, of course, but because of the vacuum around them, you are just spending you are also representing the vacuum with basis. So when you have a surface, the same thing. So you can have some problem there computationally speaking. Now you also have the numerical atomic orbitals. We call them LCAO. So that would be something that's used by Siesta. Again, I'm going to discuss that in a minute. They are very efficient. I mean, they are quite. I'm not going to say they're quite the same as Gaussian basis set. They are not, but it's a similar idea. So you represent the properties of your material, of your atoms, really, as kind of inherited from the properties of the atom, and then you can also converge. You have to be careful about the convergence. They are not super well transferable, but they are very efficient. So very often when you do a solid state calculation, if your plane waves do not allow you to do the calculation, the numerical atomic orbitals, also known as LCAO sometimes, so linear combination of atomic orbitals, will be your friend. Now, on the right-hand side, I reproduce a plot that I found in that website from the Hunt Research Group, and I find that very interesting. It's how you represent a car, for example, this simple picture. And let me give you tell a little more about this. So this is the work from the Hunt Research Group, and what they did there, and I think it's very convincing, is you can represent that car different ways. So first of all, you can have a simple basis. So this would be a localized basis, if you will, a disk of a certain radius. So you can represent your car this way. Well, you can tell that you can maybe see the shape mostly of the car, but not that great. But then you can add more bases, maybe smaller disks. That would be like adding more Gaussian, if you will. And then you can start to have something a little bit nicer. Now you can actually tell the exhaust pipe. You can start to see the wheels a little bit better, or you can actually add more bases. So this would be more bases, and you would end up you can finally see the window in the car in this case. So you can actually improve things. I really like that coming from that website, and I decided to expand this. So I wrote a couple of codes to show you how you can represent the car using different bases. So I mentioned at the beginning of the screencast the grid basis. So you can actually represent your car with a grid base. So that would be one very coarse grid. You can start to see a 10 by 10 grid. Here it's not a uniform grid, but it does not matter that much. But you can start to see the car even with just 100 points. I mean, it's pretty crude, but the advantage is that you can improve that systematically. Here is one where I I reduce the size of the grid by 2 in each direction, so it's 20 by 20. Start to be better. They can do 40 by 40. It's all systematic. Can start to get things more and more like a car. And then if you really use a lot, like 100 by 100, here you barely see the grid because the grid lines are so close to each other, but you can actually represent the car. So this is really this idea of representation. We have different options. We can represent things differently. And then I pushed this a little bit further. I wrote another little code starting still by this Hunt group picture, and I use a plane wave basis. And then in this case, I use a Fourier transform, and I just chop off all the plane waves after a certain cutoff. So this is what you would get if you just have 10 frequencies. So that would be for the Fourier transform. That's not great, right? This looks more like a spacecraft than it looks like a car, but you start to get some of the features. You can add a number of frequencies. So if you stop at 20 frequency, you can start to make up the car. Then you can add 40 frequencies. Then you can add 60 frequencies. Here you have issues with aliasing, but let's not worry too much about that. So this is basically what we can do, and I'll show you a final example later in this screencast as well. So in other words, we can have all those different methods. So the first methods with the little disk, if you will, if you want, will be like the LCAO basis, the numerical atomic orbitals. And the code Siesta is a very well-known code, very efficient, and you can do a lot of DFT calculations that you couldn't do with plane waves with Siesta, and mostly because of they really focused a lot on the basis. So they have this idea of an addition of localized of LCAO base I mean atomic orbital basis. So you are going to hear words like double zeta polarized. So DZP, for instance, in GPO as we use for this course. One of the reasons why those bases are so efficient is because they're fine and range basis sets. So you can see that on the plot on the top. So basically, there is a cutoff for those bases, after which basically the basis function is zero. Of course, if it's zero, all the integrals that involve that basis beyond the cutoff radius are going to disappear. So that makes everything very efficient. So in Siesta, you optimize your basis set. Again, there are basis set, the default basis set work pretty well. It is not always perfect. I mean, there are some numerical issues. For example, for forces, you can do forces and do molecular dynamics and phonons and things like that, but you do not have maybe the same level of control as you would have with plane waves. Talking about plane waves, many of the codes in solid state physics use plane waves. One of the three of the famous ones are VASP, Espresso, Abinit. There are many others. I don't take side here. These are just example. And then we use Fourier transform, just like I showed you the car presented with Fourier transform. So I told you it is very well suited for periodic boundary conditions. So for crystals, plane waves is really your friend. I mean, it works well for periodic systems. I mean, this is Fourier transform, so that works really well. It's actually easy to converge. I mean, if you can do the calculation, because it can be costly when you have very, very large system. You can study convergence because you just add more and more plane waves until you have results that do not change anymore. I already mentioned the disadvantages. You usually need quite a bit of plane waves to make things accurate. Um, the advantage, of course, now is that if I had given this presentation 10 years or 15 years ago, I would have told you, well, there are many things you can do, but now, of course, computers keep developing, and you can do a pretty large system with plane waves now. Uh, you can do isolated or non-periodic system, but in that case, you need really a lot of plane waves, and it becomes a little bit complicated. So let me tell you something more about plane waves, because you are likely to use plane waves at least once if you do DFT. So just this is idea here of the frequency, right? The higher the frequency, the more localized electrons you can represent. I mean, the frequency, if you have a high frequency, that means that you have a small wavelength. That means that you can have a resolution in space that's higher and higher. So a distance between peaks that's smaller and smaller, and then you can represent more and more localized stuff. So this is what I just told you. Now, if you do calculation with plane waves, you will see that you are not actually giving the highest frequency. This is not how it's done conventionally. Instead, what we use when we do plane wave calculation, we do a cutoff energy. And we can do a cutoff energy because if we consider the kinetic energy of those waves, basically the energy of a free electron, if you will, you can represent the highest momentum. I mean, the square of the highest momentum divided by 2 is basically the energy of the wave. So we typically give a cutoff energy when we do plane waves, and then the number of waves scales as the energy cutoff to the power three half. Okay. Methods like VASP, I mean, VASP is a code that's known to be very efficient, as well as GPO that we use for the hands-on part of this course. In addition to using plane waves, they also use the PO, that's why GPO comes from, right? Which is a projector augmented wave approach. Without going into details, there were very good, very interesting theorems and papers like from Blockel and others that allow to study actually to go back to this idea of pseudo-potential and how you treat the electrons, the core electrons, the one that are closer to the nuclei. And in that case, the way it's done is that those electrons are actually treated using projectors, a set of projectors. The advantage is that now we go back and having access to the wave function, including those electrons that are close to the core. So we are no longer using a pseudo-potential, we're using projectors. And that method is actually associated with the use of plane waves. Now, another method that is used, and I've seen codes, and actually I've seen code like, especially in engineering maybe, which are grid-based. So basically, you represent things on the base on a grid. You can do this just the way you treat anything when you use a grid. It's pretty good. I mean, there are quite a few people who are using them. In fact, one of the reasons I like to use GPO for this course is because GPO allows plane waves, grids, as well as the LCAO like Siesta basis. So this is nice because then you can test all three different bases within the same code. It can be high in memory and storage requirement because you are basically if you have highly localized electrons, you need to have a very fine grid, and this is a grid that you have everywhere. There's a number of challenges. I mean, mention of course everything that's very localized, like the core electrons, could be an issue. You can study the convergence with grid spacing, but very often you need a pretty small grid spacing. I find the grid-based to be useful. Sometimes it can be very efficient, so you can get a result fairly quickly if you I mean, if you accept that you do not use a very fine grade. There have been other bases that were developed. There is one that I like in particular, which is not as popular, but could be popular. It's the wavelet basis. So essentially, the wavelet, you can understand why wavelets are interesting. Okay, a wavelet is, as opposed to be a wave like a sine wave, or to be a Gaussian, which is localized. So it's a sine wave is totally delocalized. A Gaussian would be localized. Basically, a wavelet has properties of both. So it's kind of a compromise between something totally delocalized and localized. And there have been many people working on wavelets in mass. I mean, especially Doboshi's and other people. And wavelets are actually used a lot in signal processing. And so these wavelets allow you to get the best of both worlds. And people have developed that. I mean, former boss of mine, Robert Harrison, is one of the architects of Madness, which is a code using wavelets. There are other people as well who have developed Big DFT, which is another code using wavelets. It is, of course, the math is a little bit more complicated, so the development of those bases is not as widespread as plane wave or Gaussian, but this is something that's worth looking into. What is the advantage of wavelets? As I said, it has the best of both worlds, but it also allows you to have what's called a multi-resolution. So you can actually have areas of your box, if you want, or your simulation box that have a larger number of bases, more localized, less localized. So you can imagine that you have a mixture, for example, a surface, a mixture of a solid in a 2D material, in a 2D surface. In addition to a molecule, you can actually treat both of them using the localized aspect of the wavelets and the localized aspect of the wavelets. And you can have this multi-resolution in the sense that you are no longer forced to pave the space the same way like you would in plane waves. I find this very exciting. So I didn't list them on this slide, but the code that you could use is Madness and Big DFT. These are two examples. So we can actually go back to this little car, since I wrote this script as well to show you how it works. If you use a very tiny number of wavelets, here there are wavelets, but just for pedagogical purposes, if you look a tiny number of wavelets, this is what you will get. Okay, it doesn't look like a car, but it's not the idea. The idea is that you already have a multi-resolution here. So you can see that even with a tiny number of functions, you are describing things differently in space. Nobody uses 10 functions. It's just to show you. So if you use 100 functions, you start to have something a little bit better described, more efficient, and then you can use a very large number of functions and you get back your car, no problem. So some of you may say, oh, it looks exactly like JPEG 2000. Well, actually, JPEG 2000, which is a very efficient way to compress images, is exactly based on the use of wavelets. So that's something that, so the standard JPEG 2000 using wavelets. So finally, just to tell you a bit summary of where we are, if you want to use those different basic sets, you can use plane waves. That would be the first mode in GPO. The second mode, FD, means finite differences. That would be a grid base where you give the size of your H, which is the grid spacing. And then LCAO, which is like siesta, if you will. And in that case, you can use like in double zeta polarized would be kind of representation. So you can use all of them. You can, if you are able to converge, you could get all of them correctly. And I think that you could test that. So I hope this overview of the basis sets is useful for you. And if you have any questions, as always, just write them in the comment section of this YouTube video. Thank you very much.